Hello, and welcome to the Data Science Institute's virtual seminar series. My name is Dr. Leno da Silva, and I'm a data science ambassador at the Lawrence Livermore National Laboratory. Data science is essential to many of the lab's key program areas. With the help of some of the world's most advanced supercomputers, we work in a variety of fields and application domains. Through basic and applied research, our data scientists are working to solve some of the world's most pressing challenges, in areas ranging from precision medicine and advanced manufacturing to energy and national security. Here at the lab, the Data Science Institute acts as a hub for data science activities, including this seminar series and other events to introduce new ideas and encourage collaboration. Speakers from other institutions are invited to share their innovative approaches with our data science community. With recordings of these seminars, like the one you are about to watch, we are reaching a wider audience than ever before. So, welcome. If you have questions or want to follow up after the presentation, check us out online at data-science.llnl.gov or send us an email at dsi-seminars@llnl.gov. Now, sit back, relax, and enjoy the seminar.
Thanks, Ben. Thank you all for being here. It's fun to be back at Livermore 8 years after I was here as a student intern, so I've not been back since then. So it is good to be back. So I am someone who works on graph algorithms and network science, and so a lot of the talks that I give, much like a lot of talks that other people in network science and graph algorithms give, starts with the slide, tells you about all the cool things that you can do with graphs and applications and why we are motivated to study them. But I'm actually not going to do that today, maybe because I'm a little bit bored of giving slides like that, and maybe you're a little sick of hearing very high-level network science motivation. So we're going to do something a little bit different today. And what I'm going to do is I'm going to start with an abstract math problem. We'll get to the data science applications. Don't worry. One of the things that I enjoy most about my research is a lot of what I do is I get to study essentially just puzzles and play games. And so we're going to sort of take things in that direction now. So I'm going to ask you to assume for a second here that you're not at a data science seminar, but we're all here for a board game club. And I'm going to be telling you a little bit about one of my favorite board games that I've played or not a board game, it's a game that I've played over the course of the past 5 years on a problem called edge-colored clustering. And this is the best that generative AI could give me of a board game. If you want a fun story later or maybe amusing anecdote, I will tell you how hard it was to get ChatGPT to produce something reasonable for this. That's the only ChatGPT image in the rest of my talk, by the way. So if I'm going to tell you about a game, I need to tell you a little bit about the rules and about gameplay and what goes into it. And so when you see pictures of a little circle, this is called a node. This is going to represent some sort of a data object that you want to cluster in some way. And when you see these convex set-like looking things that have these nodes on the inside, this is called a hyperedge. These, just think of them as sets of nodes that share some sort of a multi-way relationship. And the color means something. The color represents some sort of a type or a category of interaction. And I'll give you examples for what that could mean in data in a little bit. So here are my little pieces here. And in the game that we are going to play, you start with these nodes that have no colors, and you get to choose a color for one of those nodes that matches the color of one of your hyperedge colors. So I can color it green, I can color it orange, I can color it purple, I can choose one and exactly one color for each one of my nodes in this game that I'm going to play. And what I'm going to want to do is I'm going to want to color nodes in such a way that I get something called a satisfied hyperedge. So I'm giving you an example of 3 different satisfied hyperedges here. A satisfied hyperedge is just when you have a hyperedge of a certain color, and all of the nodes inside that hyperedge are colored in the exact same way. And so a green hyperedge with 3 green nodes inside, those are all of the nodes that are inside it. If they're colored green, that hyperedge is satisfied. Unsatisfied hyperedges are any hyperedges that contain even a single node that does not match the color of the hyperedge. Okay, and so in this last example here, you see a purple hyperedge that has mostly purple nodes, but not exclusively purple nodes, and so this is an unsatisfied hyperedge. Okay, so with all of this in mind, the game that we're going to play is I'm given a hyperedge colored hypergraph. So let me pause here for a second. The term hypergraph is a little bit less common than the term graph. Hypergraph is what you're looking at right here. It's a set of nodes that share multi-way relationships called hyperedges. If all of these hyperedges had size 2, it means your nodes are organized into pairwise relationships. That would just be a graph. But here, because more than 2 nodes can be in some sort of a relationship. This is a hypergraph. So I'm given an edge-colored hypergraph of this form, and I have to choose colors in a way that satisfies edges. But the tricky part is that hyperedges overlap in complicated ways, and so I have to play games in order to try to satisfy hyperedges as well as possible. Okay, and so this is the whole thing. That's the entire game right here. You're given an edge-colored hypergraph. I want to color the nodes. We'll talk about some variations on this problem, but we're going to be spending most of the talk talking algorithmically about what you can do to try to solve this problem. Okay, so let's play this game for the first time together on this example hypergraph. First of all, I can identify that there's this one node that is only in a green hyperedge, so it seems reasonable to color that green. Then I can maybe color these other two nodes green as well, and at this point I'm happy and we can all celebrate because I've now satisfied one hyperedge. And so I can keep playing this game for a little bit and skipping ahead, coloring a few things at once. Let me color all of those nodes purple. So I'm happy again now because I have another hyperedge that is satisfied. And I have one last thing that I can color, and I think I'll go ahead and color that purple because that satisfies one more purple hyperedge down there. And so at this point in time, what's my score for the game? 1, 2, 3, 5? Yes, it is 3. Okay, I've satisfied 3 hyperedges. What this also means is everything else is unsatisfied. And I have 2 edges right here that are unsatisfied, so I am unhappy about that. Right? I want to satisfy things as much as possible, but I cannot always do that. And so even though I motivated this problem as I want to satisfy the most edges possible, I'm actually going to be talking about the problem from the alternative perspective, which is I want to minimize the number of unsatisfied edges that I have once I've done my coloring. So I'm going to think of this as a minimizing a penalties type of an objective as opposed to maximizing the number of rewards. It's the same at optimality. Okay. Okay, so a little bit of notation right here. K throughout the talk is going to represent the number of colors in whatever hypergraph I am looking at. And so for this example, K is 3 because I have green, orange, and purple hyperedges. And R is going to represent the maximum hyperedge size, which in this case is equal to 4 because I've got this size 4 hyperedge. And the hyperedges can be of arbitrary sizes, and I just identify the largest one of them to define R. Okay. Okay, so this is just an abstract problem. It's a fun little game to think about, maybe. Why would we want to actually study this, and what does it have to do with anything related to data science, for example? So this problem, edge-colored clustering, is just a very basic formulation for clustering data, specifically based on categorical multi-way relationships. Okay, so there's a lot of different types of situations where you might want to cluster some data objects into different groups. And what we're doing now is we're clustering things based on multi-way relationships. Those are encoded by my hyperedges, and specifically multi-way relationships that are associated with a certain type or a certain category. Okay, and so clustering just means separating data objects into groups of similar items. Many reasons why you might want to do this. Here I'm specifically highlighting multi-way relationships to distinguish this from, say, graph clustering, where graph I'm only considering pairwise relationships. So the multi-way nature of hyperedges is captured by a hypergraph. And the word category, you should think of this as being another word for the type, and it also corresponds to the color. Each color will represent one type of a category. Okay, so to bring this a little bit closer to applications, let's talk about like what picture you might have in your head for what the nodes and the hyperedges and the colors represent. So for example, the node could be some author. And when you have a group of authors that publish a paper together, you can represent this by a hyperedge. And when a group of authors publishes a paper together, there's a difference between publishing a biology paper versus a computer science paper, or data mining or versus machine learning paper. And so you can think of the color as representing the type of publication. And so if you have this type of data and you solve the ECC objective on it, you can think of this as a very simple approach to trying to classify authors' fields based on their publications, for example. Okay. Another picture that we'll see more towards the end of the talk is you can think of each node as being a food ingredient. And when you combine a set of food ingredients into a recipe, you can represent that by a hyperedge. And then when you have a recipe, it could be from a different type of cuisine. And so you can think of the colors representing the type of cuisine that food is. For example, Italian or Cajun food or Korean food or any other type of cuisine. And so in this case, edge-colored clustering, you can think of it as partitioning your ingredients to different cuisines in order to maximize the different types of recipes that you can make by partitioning the ingredients in this way. One other example, you can think of a node as being some worker, someone who is capable of doing some tasks, and you have a set of tasks that you would like to accomplish potentially. And so a task is a hyperedge, or a group project is a hyperedge, and you need a certain set of specific people in order to accomplish that. Now you can think of the color as representing a project type, or I actually like a little bit more the idea of thinking about it as a location. I take all my workers and I separate them to different work sites. So you're allocating your workers to different work sites, and once you've allocated people to different work sites, there are certain jobs that you can accomplish after you sent those people to those places. So you can only accomplish jobs of a certain type. So if I'm a green worker, I can go to the green work site and I can accomplish stuff there. And so I want to partition people into different work sites in order to fulfill a lot of different types of projects. And so that's what edge-colored clustering would give you in that context. And there are other examples as well. Okay. A lot of my work is theoretical. So I like the applications, but also just like thinking about a problem from an algorithmic and theoretical perspective. So the first thing that I want you to know about edge-colored clustering is that this is an NP-hard problem. And so you're not going to be able to find an efficient approach to solving this optimally. And so what we're going to do is we're going to turn to approximation algorithms. So years ago, this was first introduced specifically in the graph case. And so there was some work on approximation algorithms for the graph case of this problem. And then as I have motivated, I'm more interested in the hypergraph version because I want to think about multi-way relationships, group projects, group publications, things like that. And so I'm going to be telling you kind of a little bit about a couple different things that I've worked on related to the hypergraph focus. And I want to thank my co-authors for the work. One of them is here in the audience. Tommy has worked with me a little bit on this problem. There's some other people, too, I've had the pleasure of working with on these problems. Okay, so I first want to clarify, when I say approximating the problem, what type of an algorithm, what type of a guarantee we want. So this is a traditional type of guarantee when you're seeking approximation algorithms. When I say something like I develop a 2 approximation for a problem, that would mean, for example, that if the optimal solution is to only leave 4 hyperedges unsatisfied, a 2 approximation is guaranteed not necessarily to find the optimal solution, but I will at most leave 2 times 4 equals 8 edges unsatisfied. Okay, and so I'm blowing up the optimal solution by a bounded amount. And now what I want to do is I want to design a polynomial time algorithm that has a C approximation guarantee where C is as close to 1 as possible. 1 would be I'd optimally solve it. Okay. Okay, so let's pose some algorithmic theoretical questions that we might want to tackle. So first of all, what's just the best polynomial time approximation algorithm that you can design? Okay, so the only bound on the runtime is it needs to run in polynomial time and size of the input. And I'm going to be telling you a little bit about some results that are based on a linear programming relaxation. And it turns out this is the most successful approach that has been designed in terms of the best approximation factor. But I'm also interested in designing approximation algorithms that are especially fast. So it's not enough for it to be polynomial time. I want the approximation algorithm to run in linear time in terms of the hypergraph. So to clarify, when you say linear time in terms of the hypergraph has nodes, it has edges, and the edges have different sizes. So when we say linear time, linear means it's the sum of the sizes of the edges. And a way to intuitively think about this is the time it would take to just read in the input and store it. Okay, and so I want algorithms that will run asymptotically, at least in terms of this amount. Okay, so fast algorithms. We'll also talk just a little bit about different variants of the problem that are worth studying. How can I develop, once I've sort of answered question 1 and 2 for the basic edge-colored clustering problem, what are other variations of the problem that you could consider studying and trying to tackle with the algorithmic techniques that I'm going to present to you today? Okay, and then we'll also see some concrete empirical results on some data sets. Okay, so in particular, I'm going to tell you just a little bit about 3 different algorithms. The first is a slightly better than 2 approximation algorithm. So you take the smaller of 2 minus 2 over k, or 2 minus 2 over r plus 1. Remember, k is the number of colors, r is the maximum hyperedge size, so you get to choose whichever of these leads to a better approximation factor. And this comes by rounding a linear programming relaxation that I'll tell you a little bit about. As far as fast algorithms, I will briefly mention an R approximation algorithm using a very simple, greedy linear time algorithm. So R, again, R is the number of nodes in the maximum hyperedge. So if R is small, this is reasonable, but R could be very large. So this is maybe not a great approximation guarantee. And we'll spend a little bit more time talking about how you can actually get a 2 approximation. So it doesn't depend on R, doesn't depend on K. You can get a 2 approximation also in linear time by drawing connections to a problem called vertex cover. And we'll talk about that. Okay. I want to just briefly mention that it turns out the first algorithm and the last algorithm, they're tight, or in some sense the best possible that you could obtain with respect to certain lower bounds. So there's some interesting stuff going on there that I'm happy to talk to you about offline. But for the purposes of this talk, we won't really get to it. Okay. Okay, so ask me later if you're interested. Okay, so what I want to tell you first about is these linear programming relaxations for edge-colored clustering. In order to tell you about the linear programming relaxation, what I first want to tell you about is how do I just encode optimal solutions to this problem by setting up a mathematical optimization problem. So let's translate these pictures, these hypergraphs, into some mathematical optimization problem, and then we'll relax it to get this linear program. Okay, so I have this green-colored hyperedge of size 3 with nodes u, v, and w. And what I'm going to do is I'm going to introduce a variable for every node color pair. So here, node v, color g, green. yvg is going to equal 1 if I want to give node v color g. And otherwise, you can think of it as being 0. Okay, so it's either 0 or 1 if I give that node the color or not. yug0 means node u is not given color g. In this case, that's because I've given it color purple. Okay. And then I can encode the fact that every node gets exactly one color by summing up all of these variables for one node. So I fix a node v, and I sum up all of the color variables for that node. It equals 1. This translates to saying node v can get exactly one color. It gets one color and only one color. Okay, so I have these variables for nodes and colors. I'm also going to introduce this variable xe. That's going to be equal to 1 if e is not satisfied. So it equals 1 if I make a mistake or I leave it unsatisfied. Okay. So with that, the objective of edge-colored clustering is I want to minimize the sum of these xe variables, right? Because these are all either 1s or 0s, and so the number of them that is 1s, that means I made an unsatisfaction there, and so I want to minimize unsatisfaction. And now at this point, what I need to do is I need to couple the relationship between the node variables and the edge variables in order to set up this optimization problem. So I'm going to do it as follows. For every node, so node v is in an edge e, I'm going to set up a constraint of the form xe is greater than or equal to 1 minus yvg. Why is this the right constraint? Well, notice in my example, yvg is equal to 1 because I did indeed color node v color g. And so what this is saying is this lower bound says that xe is greater than or equal to 0. And in particular, that means that xe can be equal to 0. And if it's equal to 0, it means I'm happy. I didn't leave that edge unsatisfied. xe wants to be 0. And this constraint says, as far as I'm concerned, you can be 0 because v is colored correctly for this edge. Similarly, for node w, I get this constraint to be xe is greater than or equal to 0. So I'm all good. I'm happy. However, what breaks things for me is the fact that yug is equal to 0 because I did not color node u color green. And so this constraint tells me that xe is greater than or equal to 1.
Online?
Yes.
So Goran asks, what constraint is there to prevent one from assigning every node the same color and thus satisfying every hyperedge?
If you set every node the same color, you will satisfy every hyperedge of that color. But remember that the hypergraph is formed of hyperedges of many different types of colors. I have, in the example that I gave before, I can even go back to the picture right here. If I assign all of the nodes to be purple, I satisfy 2 purple edges. I don't satisfy all the hyperedges. So that would satisfy all of the hyperedges of a particular color, but it would not satisfy all hyperedges. And so I have to be careful to balance things out. Okay. Thanks for the question. But it is absolutely true that if I only cared about one color, this would be trivially easy to solve. But since I care about all colors, it makes it more complicated. So yeah, so locally right now, for this if you're only looking at this hyperedge, it seems silly to color that node purple. But what you should think about is node u is maybe in several other purple hyperedges, right? And so there is some motivation to actually color that purple. Okay, okay, so I've set up this set of constraints in these variables. And notice right now, xe is going to just be as small as it possibly can be because I'm minimizing the sum of xe's. And so xe is only going to be able to equal 0 if all of the nodes in E have the right color as far as this hyperedge is concerned. Okay. Okay, so putting all these pieces together, I have this optimization problem where I'm minimizing the number of unsatisfied edges. I'm ensuring that every node gets one color. And I've got these constraints to ensure that hyperedge E is left unsatisfied whenever it contains a miscolored node. Now, if you think of this variable yvc, which encodes how much node v belongs to color c, if I force this to be either 0 or 1, this is the original problem. It's the same problem that we started with. It's exactly the edge-colored clustering problem. Okay, so if I can solve this integer program, or this binary linear program, I've optimally solved my problem. However, remember, this is the NP-hard objective, so I'm not actually going to be able to solve that. And so algorithmically, what we do is we relax this into a linear programming relaxation, where instead of saying that my variables are going to be either 0 or 1, I allow them to be anything between 0 or 1. And so this has the advantage that I can solve linear programming in polynomial time. And so I can actually now, in polynomial time, get a solution to this optimization problem. But now I'm solving a different problem. I'm not giving every node a color. I'm giving all the nodes fractional colors. And so you can think of this as saying, well, I believe this node is half purple and 1/3 green and the rest of it's orange or something like that. And so now the task at hand is I have this fractional set of colors, and I need to find a way to round this into actual one color per node in order for this to actually address the problem of edge-colored clustering. And I want to do this in such a way that I'm not too far away from the solution, the optimal solution to the linear program. So in particular, by relaxing the objective in this way, I can guarantee that the sum of these xe variables, now these xe's can be fractional, whatever the sum is, it's going to be a lower bound for the optimal objective. And that's going to be useful for designing approximation algorithms. Okay. So the analysis of the approximation algorithm spans many, many pages, and we're not even going to attempt to go through a proof. However, I will illustrate for you what ends up being sort of the best approach for rounding this linear program. So let me give you the rounding algorithm. And again, this is happening for all the nodes in the hyperedges, but I'm just illustrating it for one hyperedge. The first step is I solve the linear program and I get these fractional colors. Okay, and so here in this hyperedge, I've got these different fractions for all of the nodes in this hyperedge right here. And this is going to be a randomized algorithm. So my first step is I'm going to generate a random priority order for the colors. Okay, so for example, this is drawn uniformly at random. And so when I do this one time, let's say, for example, it says green is the most important color, followed by purple, followed by orange. Now save that information for later. I'm going to introduce more randomness somewhere. I'm going to generate a random threshold t. It's going to be some value between 0 and 1. Actually, sometimes I'm going to restrict it even more. But once I have this random threshold, let's say, for example, it is 0.31, I am then going to compare the color node variables to that threshold. And for example, I'm going to say that yvg is greater than t means that color g wants node v. And I'm going to do this for all the other colors as well using the same threshold. Okay. So for this particular example, notice that all three of these nodes have a pretty high fraction for green. In particular, all of these numbers, 0.5, 0.33, 0.75, it's above the 0.31 threshold. So all of these nodes want to be colored green. But the trick is a couple of them also want to be colored a different color because the fraction for that color is also larger than 0.31. Okay? So all these nodes want potentially more than one color, and this is why I generated a priority of the colors. So at this point in time, if I have to break ties, if a node wants more than one color, then I'm just going to give that node to the highest priority color that wants it. Okay? And so in this particular case right now, I end up satisfying the edge because all of the nodes want green, and green is the highest priority color. Okay, and so yay, I'm happy. But this is a randomized algorithm, and so if I run this many different times, I could get different types of solutions. Okay, so if I do this again, maybe purple is the highest priority, maybe t is equal 19. What you'll see if it comes up again is we have all these nodes wanting different colors, and now I'm just going to give each node to the highest priority color. And in this case, even though all the nodes want green, they don't all get green because purple has a higher priority, and V also wants purple. Okay, so I'm not satisfied there. So we can keep doing this for a little while. The point and the main proof technique in order to show that this is an algorithm that satisfies an approximation guarantee is there's some tricky details in figuring out how to choose the right threshold. You can't just choose any old value between 0 and 1. It turns out you have to bound the interval, and you have to do some detailed analysis. And at the end of the day, after you spend several pages working on this, you can prove that for any one edge, the probability of leaving that edge unsatisfied is bounded. And it's specifically bounded in terms of this amount. So for an edge E, the probability of making a mistake at it is bounded in terms of this fraction, or this approximation ratio, times the LP variable for that value. Okay? So there's a lot of work that goes into this. And even after that, you have to say a few more things to get to the final result. But it turns out that this factor right here, this is the approximation guarantee that the algorithm satisfies in expectation. In expectation, you will make it that many more times mistakes than the optimal solution will make. Okay, so there's still more details. but it turns out that if you can prove this result about the probability, you can push it through to prove that this is a 2 minus 2 over k approximation or a 2 minus 2 over r plus 1 approximation, whichever of those two things is smaller. Okay. So this is technique number one, and this is the best approximation result that exists for this problem currently. But what if I want one of these really fast algorithms? Okay, and so linear time algorithms, things get a little bit more tricky because I can't solve a linear program. That's more expensive than linear time, even though it is polynomial time. So first algorithm that I developed with some co-authors a while ago, it's an algorithm very simple. We called it majority vote. You take one node and you just look at all of the hyperedges that is contained in. You look at all of their colors. In this particular case, V is in 3 purple, 2 green, and 1 orange hyperedge. And since purple is the most common, then I'm just going to go ahead and assign it to be purple. Okay, so it's this very myopic, simple approach. You can implement this very quickly. It ends up being linear time. We didn't introduce this to be like a really meaningful algorithm. It was more like we want a very simple baseline algorithm. And it was only afterwards that we looked at it more closely and we were able to prove that it actually is an R approximation algorithm. So it satisfies an approximation guarantee. But again, if R is really large, this is not going to be great. Okay. More interestingly, though, a couple years ago, thinking about this problem again, I was able to realize that there is a connection to a problem called vertex cover. And if you are careful about the way you use that connection, you can design a much better linear time algorithm. So its approximation guarantee is not quite as good as you get from the linear program. It's not less than 2, but it is exactly 2. And it doesn't matter how large the hyperedge is. And so I'm now going to spend just a little bit more time telling you about this other vertex cover-based algorithm. Okay. Now, in order to do so, I want to tell you some background about vertex cover. So this is one of the most well-studied NP-hard problems. It was one of CARP's original NP-complete problems. So in the vertex cover problem, you have a graph. It's a bunch of nodes that share these edges. And a vertex cover is a set of nodes that covers all edges in the sense that if you look at any one of the edges here, one of those edges has a blue endpoint, because blue for me is going to represent a covered node. Okay. So the goal is to find a minimum-sized vertex cover. And I'll just mention that if you look at all of the nodes that are not in the cover, these form something called an independent set, which is to say that they don't share any edges. So the opposite problem or the dual problem is finding a maximum independent set for this problem. Okay. Super well-studied problem to the point where long before I was born, people had designed very fast two-approximation algorithms for vertex cover. Very fast and very simple algorithms. And so this has been known for a really long time. I'm going to tell you about one specific algorithm that was not designed in the 1970s and 1980s. So this is also separate work. There's this simple algorithm for finding a maximal independent set called greedy maximal independent set. And it works as follows. It's a randomized algorithm. I generate a random permutation on all of my nodes, okay, like the one you see right here. And then I visit all the nodes in that order. So I first visit node number 1, then node number 2. And when I'm visiting a node, if I can add that node to an independent set, I do so. So for this picture right here, if I can make a node green, I will make it green. And if I visit a node, I cannot make it green if it's already touching a green node. Okay? And so I'm going to put as many nodes in the green set, the maximal independent set, as possible. And so I just do that greedily after I have ordered the nodes. And then I just march through and I visit them all. Okay? So I is green. It's an independent set. C is a vertex cover. This algorithm itself has existed for a long time. And I realized a couple years ago that it turns out that in expectation, the cover that you get from this algorithm is a two-approximate vertex cover. And anecdotally, I discovered this accidentally. It's now one of my favorite results I've ever worked on. But I actually discovered accidentally while trying to design approximation algorithms for edge-colored clustering. Okay, and so you'll see in a couple slides why this algorithm can be useful for edge-colored clustering. But for right now, it's just a background on vertex cover. And that's one algorithm that will allow you to get this two-approximate solution to the vertex cover problem. Okay. So what does all of this have to do with edge-colored clustering? We're going to come back and we're now going to think about the problem in a different but equivalent way. So now my goal in edge-colored clustering, I'm going to cast it as follows. I want to delete the minimum number of edges so that everything that remains can be satisfied. So in particular, if I delete those two edges, everything that remains can be satisfied because every node belongs to exactly one color. Okay, and so this is just a different way to state the same problem. I can satisfy everything that remains, and my objective function is 2. My penalty is 2. Okay. Yet another way to think about the problem is as follows. I want to delete a minimum number of edges so that there are no more bad edge pairs that remain. And a bad edge pair is just going to be two hyperedges that have different colors and that have non-empty intersection. So in this case, because there is a node that is both in a green hyperedge and an orange hyperedge, I can't color that node both green and orange. So therefore, I'm going to have to delete one of those edges or the other. Okay, so there are a lot of different bad hyperedges, bad hyperedge pairs. Okay, and so I know that in each one of these bad hyperedge pairs, I'm going to have to delete, or I can think of it as cover, one of these two different hyperedges. Okay. Yes? What do you mean the bad? Yeah, so the question, I can just restate the question here. What do I mean by bad? I mean bad because I don't want to delete hyperedges. So I think of it as bad as having to delete hyperedges. And when I have two hyperedges that are different colors and they have an intersection this is bad because it indicates I'm going to have to do something that I don't like, which is delete one of them. Right? So that's the only reason I'm using the word bad here, because deleting edges, I'd rather avoid doing that, but here's a situation where I'm going to have to delete something. So these things make me unhappy, so I call them bad. Okay, so here's the relation to vertex cover. Take my original edge-colored clustering problem, and now what I'm going to do is I'm going to convert this to an instance of vertex cover. So I'm, first of all, going to think about replacing every one of my hyperedges with a node. So hyperedges A, B, C, D, and E turn into nodes G, B, C, D, and E in some graph. And now every time I identify a bad hyperedge pair in my original hypergraph, I'm going to draw an edge between the respective nodes in my new graph that I'm constructing. Okay, and because there are other bad hyperedge pairs, I'm going to introduce some other edges in this new graph G. And then once I have done this conversion, what I'm going to do is I'm going to find a vertex cover, in particular a minimum vertex cover of my graph. So I will find these two nodes to cover. Right? So every edge has to have at least one red endpoint. And if I cover a node in G, that exactly means I'm deleting that hyperedge in the hypergraph. Okay? And so I'm reducing the hypergraph problem to the vertex cover problem. And it turns out you can do this in such a way that an approximate solution to the vertex cover problem in G is exactly an approximate solution to the hypergraph edge-colored clustering problem. Okay. So what I can do right now, at least a naive approach, is I can just explicitly construct this graph G, actually form it, and then run an existing fast algorithm for it, and I get a 2 approximation for edge-colored clustering. Now the downside of this is if I actually spend the time actually forming the graph G, I don't get a linear time algorithm. It turns out it's not as fast as I could make it. And you don't have to worry about the details about this runtime right here, but it's not as fast as I would really like it to be. This is not yet a linear runtime. I can, however, get a linear runtime by being smart about implementing an algorithm without actually ever forming the graph G. So it's like I want to run an algorithm on G, but I'm never going to form G. I'm just going to apply that algorithm directly to H. So this is where this greedy miss algorithm comes into play. Okay, remember, I'm just ordering my nodes by some random permutation, and I'm greedily leaving nodes uncovered. I'm putting them in an independent set. I can implement this for edge-colored clustering without ever actually forming the graph on the right. Okay, so what this algorithm means for edge-colored clustering is I visit my hyperedges in order, and when I visit a hyperedge, if I can satisfy it, I satisfy it. And what that means is I color all of the nodes the same as the color of the hyperedge. And that's exactly the same thing as applying the greedy miss algorithm to the graph on the right, but I never actually form the graph on the right. I don't have to. It's inefficient and there's no point. And so now this greedy miss algorithm, notice that what I'm doing is I'm visiting each edge, and when I visit that edge, I just have to check each node and see if it's colored or not. And so that takes exactly O of size of the hyperedge time, and so overall this ends up being linear time because it's just the sum of the sizes of the hyperedges. And so now I have my linear time algorithm. Okay, you take a deep breath. We've made it through the more technical sides of the talk. If there are any, I'm happy to answer questions at this point in time. But otherwise what we're going to do is we're going to do something which I hope you'll find a little bit fun, is we're actually going to talk about running this on some experiments and seeing what we get by implementing edge-colored clustering algorithms and running them in practice. Yes, I know there's some microphones, so maybe we'll.
So the greedy MIS algorithm, in practice, the order in which you randomly choose them matters a lot. I know it doesn't for the approximation guarantee, but the quality. How much have you experimented with the order, and are there heuristics to order things instead of just uniformly random?
Yeah. This is, so an interesting question here that's related to your question is, how do you de-randomize this? Can you find a way to not just say completely at random, I'm selecting a node, and then I'm putting that in the order? I have not explored this very far, although I'm not sure if you know this, but Lance Flexer did a project where he tried different orderings. So Lance Flexer is also someone else who's at Texas A&M and has connections to the lab here, and he's done a project on different ways that you can order the nodes. And I think that in practice, it tends to do pretty well if you look at like high degree nodes or low degree nodes. I forget which one ends up being better, the high degree nodes or the low degree nodes. But there's a little bit of a trade-off there, because if you choose that in practice, it often performs better. But you can also create pathological examples where it does horribly. And so there's this trade-off. If you select a deterministic way to choose nodes, often it's better in practice, but in the worst case, it's much worse. So there's still some directions you could explore in terms of, is there a way that we could do better on average that doesn't lead to a worst case approximation guarantee?
I had a general question on the solutions and if they're unique solutions, and how do you approach them if there are multiple solutions?
So the solutions are not unique. So this is a good observation. There could be a lot of different node colorings that lead to the same approach. I solve this by ignoring that problem altogether, as is often the case in algorithms research. You say, I have this combinatorial problem. Quite often NP-hard combinatorial problems have multiple solutions. And I'm just looking at, there is a unique number of edges to delete, which is the optimal solution, and we're just purely looking at the number of edges that you delete. Now, in practical applications, you may care. So there are different variants of the problem. They kind of get at satisfying different types of colors and things like that. But largely, that's ignored so far. And that could be another interesting thing to explore in more depth if you have an application where you really care about that.
I have two questions. The first one is, I mean, in a lot of real-world applications, it oftentimes happens that probably one or two of the edges are much more important than the other ones. Probably some are much more important than the other relatively. So is there a way to like put weights on the optimization so that, I mean, the nodes are having much more weights to the, you get what I'm saying, right? So the nodes get much more weights to some of these edges, and some of them they don't.
This is a fantastic question. I'm glad you asked it, because it turns out all of the algorithms I presented, I can do the same things for the weighted case, and it works just as well. The reason I did not put a weight is because I'm trying not to bog anyone down with extra notation. So the idea that has worked here for the unweighted case, with very slight tweaks, you can make it work for the weighted case. And so actually that's a nice thing about this problem. Sometimes when you look at the unweighted version of a problem and a weighted version of the problem, there are massive differences in computational complexity. That's not the case for this problem. We can do all of this in the weighted case as well.
Okay, thank you. That's good. And my second question is, all of this looks pretty deterministic. So my question is, can we make this probabilistic in the sense that instead of setting these nodes or these data as one color, maybe it gives you a probability of being in one of these colors or one of these edges, and so the entire problem turns into like a likelihood, as like maximizing the likelihood overall, rather than minimizing the number of incorrect predictions.
Yeah, so I mean, I guess the first thing that pops into my head is when you're solving the linear programming relaxation, you're sort of exactly solving that problem. If I allow my nodes to have fractional colorings, in some sense this makes the problem easier, because you can sort of like, I don't have to choose to be purple or green. I can just be both of them. And so in that sense, we sort of already have that. Now, maybe there's some formulation of the problem where you want something a little bit different than a linear programming relaxation, in which case I'm not sure quite what the answer would be. I can tell you we've done some work on overlapping versions of the problem where a node can be given multiple colors, and that's slightly different than just solving the linear programming relaxation. But if you just want fractional colors, solve the linear program and then you've got that.
No, look, I was thinking more on the terms of like an inference problem, like a Bayesian inference problem or some probabilistic inference problem where we maximize some probability instead of like minimizing the number of incorrect edges.
So you could maximize the number of satisfied edges. You could turn this into, this is a good question, and there are connections to something that I may get to at the end of the talk where they have much more of an inference type approach. Okay. But I believe that there's probably ways that you could formulate this as a maximum likelihood inference type problem. And that would end up being probably sharing close relationships. It would just be maybe a little bit different way to think about the data. I'm thinking about my data as coming from some distribution. I make some assumptions about that distribution. Interesting questions. I don't have a good short answer for you, but thanks for asking it.
For the linear programming relaxation, you have a bound with a certain formulation. Have you tried different formulations? For instance, the vertex coloring gives you another linear programming formulation. Mm-hmm. Sorry, the vertex coloring, there is the graph cover that gives you another formulation. There are many formulations.
Yes.
So is the goal to have like the strongest linear program that is in polynomial size so you can get the best polynomial bound? Or have you tried other formulations or not?
Yes, fantastic question. The answer is yes. We've thought about a lot of different linear programming relaxations. So the linear programming relaxation, you could just think of this as, cast it as a vertex cover. Vertex cover has its own linear programming relaxation. I can tell you it's a weaker linear programming relaxation than the linear programming relaxation that I presented. So in particular, that one has an integrality gap of 2. So basically, if you use that approach, you're not going to be able to do better than a 2 approximation. However, if you use the linear programming relaxation that I introduced, you can get better approximation guarantees because it's a tighter lower bound. Whenever you do a linear programming relaxation, the optimal solution is here. An LP relaxation gives you a solution down here. It's a lower bound. And there are several different linear programs that we've considered for different versions of the problem, and they all have different relationships in terms of how close they come to bounding the lower solution. But then also there are advantages in terms of, it turns out the linear programming relaxation you get from vertex cover, it has nice properties like it's half integral. All of my variables are 0, 1/2, or 1, and it turns out we can leverage that to design faster algorithms for certain cases. And so this has actually been an active area that I've been working on with some students since then. But fantastic question. The answer is yes, we have been thinking about these things too.
I have a follow-up question from online concerning the weighted case of the problem. Mm-hmm. So when you're talking about weights, are you talking about weights on the nodes or on the edges themselves?
Great question. The weights on the edges. So the idea being like if I have a hyper edge that I want to satisfy, how strongly do I want to satisfy it? Or in this version, how adverse am I to the idea of deleting this hyper edge? So it's weights on the hyper edges specifically, not on the nodes. Okay, great questions. Thanks so much for them. I do want to save some time for what I think you might find somewhat interesting. So let's talk about what we can get on some real data. And so kind of just for some fun right here, we're looking at this Kaggle data set that was introduced a while ago as a classifying recipes challenge on Kaggle. And so the data is a bunch of recipes, and each one of the recipes is made up as ingredients. And so the original challenge was they wanted to classify the recipes into their cuisines based on the ingredients in them. And I'm ignoring the original challenge. I apologize here that we're having some technical difficulties. But what I'm going to do is I'm going to not hide the labels and try to predict them. I'm just going to look at the labels for the different cuisines. And then I'm going to model that as an edge-colored hypergraph. Okay, so think now just the edge-colored hypergraph again. A node is a recipe, and a hyperedge is a set of nodes that are. Sorry, I said a node is a recipe. A node is an ingredient. A hyperedge is a set of nodes that go into a recipe, and I'm just going to look at the colors, and the colors represent the cuisine. Okay, so in this case, like this green looks like it represents. I think that might be like pico de gallo or something like that. And so we're going to say the Mexican is the green color, and so these colors are associated with green, right? So the goal of ECC is basically I'm allocating ingredients to different cuisines to try to maximize the number of recipes that I can make or minimize the number of recipes that I'm not going to be able to make. And I want to point out right here, first of all, that there's a lot of ingredients that I really should not think of as belonging to one cuisine, right? Like no one owns the ingredient salt or oil. And so we have this threshold beta, and beta, it just means that for different choices of the threshold, I will throw out some ingredients based on how common they are. Okay, so I have some way to order the nodes based on how common they are, and I just choose some beta threshold, and I throw away the most common ones, and I try to satisfy what remains. Okay, so what we're going to do is we're going to have a cook-off. So we are going to compare Chef LP, which is the algorithm for edge-color clustering that's based on this linear programming relaxation, and we're going to compare this with Chef majority vote. So these experiments were actually run before the vertex cover-based approach was around, so I don't have that comparison here, but I hope this one will still be somewhat interesting. So I'm comparing these two things, and just for the first thing I'm going to do is I'm going to create a plot right here where in the x-axis, I'm just varying this threshold. So in the x-axis, I'm just varying the number of ingredients that I throw away, and then I look at how many of the rest of the recipes I can satisfy. The y-axis is the edge satisfaction, which is just to say the fraction of recipes in the data set that you can make using these different algorithms. And so red is majority vote, and blue is the linear program. And as you can see, that the blue line is always above the red line, which means that the linear programming algorithm is doing better, actually making dishes, satisfying hyperedges. Okay. We can also think about the food waste, which here I am classifying in the y-axis as the number of unused ingredients. So an ingredient is unused if I assign it to a certain cuisine, but then it doesn't actually help me make any dishes. Okay, and so I'm going to call that an unused ingredient, and it turns out again that we see lower is better here. I don't want food waste. I don't want unused ingredients, and so the linear program is doing better with the ingredients that it has than the red chef majority vote. Okay. If we break things down into each one of the cuisines in more depth, so here you can see the different cuisine types: Italian, Mexican, Southern U.S., Chinese, etc. This first column right here, this delta I, it's the ingredients that one chef gave to this cuisine that the other chef did not give to this cuisine. So if you look at the first row, you can see that the linear program assigned 171 ingredients to the Italian cuisine that the MV approach, the majority vote approach, did not assign to that cuisine. Okay, so they're doing things in a different way. So this is the number of ingredients that one gave the cuisine that the other one did not. This change in R is the number of new recipes that one chef can make that the other one cannot make based on these new ingredients. And if you take the ratio between these two, lower is going to be better because it means the algorithm is able to make far more recipes by only changing a small number of ingredients. And so a smaller ratio here is better. And so if you just take a glance here at the results, what you're going to find by and large is that the delta I tends to be well, the delta I and the delta R is not, sometimes it's larger and sometimes it's smaller. But the point is the ratio tends to be smaller overall for the LP because it is putting recipes, or is putting ingredients in different cuisines better in a way that it can satisfy more recipes. And so this is just half of the cuisines. There's the other half, and you can see the same basic trends there going on overall. Okay. Let's take even more careful look at individual types of clusters that were formed. So there's one cluster for each type of cuisine. Okay. So in one case study, we're going to consider all of the ingredients and the recipes in the Irish cluster as made by LP versus MV. So in this particular case, if you set your threshold beta right in a certain way, the LP will give 15 ingredients to the Irish cluster that majority vote does not. And here are some of those examples: biscuit mix, decorating sugars, peppermint extract, Oreo cookies. So you can start to imagine whether you're seeing any types of patterns in this data. And the linear program uses 12 ingredients. It actually uses them, so it puts them in actual dishes that the majority vote algorithm does not, including mint chocolate chip ice cream, instant pudding mix, butterscotch filling, and Jimmy's, which I actually had to look up as just another word for sprinkles. So maybe you knew that, but I did not. And then there are 15 recipes that the linear program can make that the majority vote does not. 10 of them are desserts, and so what's kind of fun is this is sort of identified an Irish dessert cluster, and perhaps even more interestingly, the color green shows up disproportionately a lot, and so I think of this as the St. Patrick's Day Irish dessert cluster that one chef discovered that the other one did not. If you play this game with the French cuisine, the linear program has 24 ingredients that majority vote does not. Here's some of them: red grapefruit sorbet, strawberry ice cream, dry hard cider, etc., etc. There are 15 ingredients that are used by the linear program that majority vote does not, including dessert wine, eau de vie, vanilla sugar. And if you look at the number of recipes that are made, there are 24 recipes that the linear program makes that majority vote does not. 18 of them are desserts, and of those desserts, 14 of them have a very significant fruit-based component. And so if you look at the patterns right here, Chef LP is cooking up a bunch of fruit-based desserts. So this is the fruit-based dessert cluster. Okay. British cuisine, there are 15 ingredients that LP puts in this cuisine, this cluster that majority vote does not. And to kind of jump to the chase on this one, it seems like most of these are beef dishes. And so there's another interesting patterns. My particular favorite was the Brazilian cluster. We saw this pattern over and over again for different thresholds that we looked at. this beta threshold for the number of ingredients you throw out. We kept seeing the same pattern. The linear program has 10 ingredients that majority vote does not. Simple syrup, light rum, ice, superfine sugar, key lime, cocoa, kumquats, liquor, mango nectar, and vanilla essence. And it uses all but one of them. Or actually, it also, separately from that, if you look at all of the ingredients that either of them put in the clusters, there are specifically 9 ingredients that LP uses that majority vote does not use. Are you seeing any patterns here? Hibiscus flowers, frozen banana, acai, liquor, fruit puree, chia seeds. Brazilian cocktails. Yes, so it turns out there are 23 recipes that LP makes that MV does not. One is a smoothie, and the other 22 of them are super closely related. They're all a combination of cachaça, ice, and lime. Do you have any Brazilians in the house or anyone who knows what this is? It's a caipirinha, yeah. So this was particularly fun for me because when we were first studying these clusters, my co-author had just come back from a conference in Brazil. And so I had not heard of a caipirinha, but it was kind of funny. I showed him these results, and he's like, oh, I had one of those last week. That's a caipirinha. And so that was pretty fun that we detected the Brazilian caipirinha cluster in our data. So we got a kick out of that. I'm about out of time here. So there are some other results on a Trivago data set where the vertex cover-based approaches do well. It's much faster than the linear program, about as fast as majority vote, but does much better in terms of approximation. I can tell you more about that. The summary of the algorithmic results here, linear programming relaxations, they are polynomial time solvable. They lead to good results in practice. They're not the very fastest. There's a fast, greedy strategy. But it doesn't perform super well, especially when R is large, and you can get really good empirical results as well as better theoretical guarantees once you draw this connection to vertex cover. There are other variants of the problem that are worth studying, and we've done that just a little bit. I just want to give you a taste of different directions we've gone since then. Remember, in particular for the ingredients experiment, we know that salt doesn't belong to one cluster, neither does olive oil, and so this motivated us to study this and other types of applications, motivated us to study an overlapping variant of the problem, where you might want to put different nodes in multiple clusters at once. You still don't want to put all nodes in all clusters, so you want to have some meaningful bound on overlap. And so we designed some new approaches that were largely based on this linear programming technique. And so the same type of technique worked well in that case, and that led to a paper last year at Wisdom. More recently, we studied balanced and fair versions of the problem. And so in this example right here on the left here, there's a hypergraph where 4 edges are satisfied. You can't see right now, but 2 of them are blue, 2 of them are red, none of them are green. If there's an application where I want to somehow balance things, like for example, I could satisfy 1 edge of each color. So my total score in some sense is 3, but it's fair. It's more balanced among the different types of colors. You can design approximation algorithms. And so we designed a 2 approximation for this. And it has some connections both to LP rounding as well as to a variant of vertex cover. And so some of the same connections and algorithmic techniques are working. And if you're interested in more details, you can go ahead and ask Tommy for more details. He'll be here all summer, so do pick his brain about this one. If you're interested in hearing a connection to a different problem that was studied by Richard Darling and a few other colleagues, you can come see me afterwards, but at this point you've been listening to me for a while. So rather than maybe going into depth about that, I'm just going to go ahead and skip over this and say, here's some papers if you're interested. There's software available for all of these different papers. I again want to thank all of my co-authors, and thank you for your attention. I'm happy to take any questions.
Thank you for the great talk, Professor Belt. I'm also from Texas A&M. I'm PhD students in statistics.
Awesome.
I really like your application in recipe and ingredients. And motivated by that application, I have 2 questions. It's more related to like the variance version of this model. For example, when we're cooking, sometimes there's alternative ingredients to it, or sometimes we have more than one unit of each ingredient. So if we map that application back to the basic model here, so have you ever considered situations when like the node can be copy, like for multiple times, like multiple ingredients, or if there's any alternative for that specific node or that set of node can be replaced by other set of node.
Yeah, thanks for your question. And gig 'em, go Aggies. As far as the repeating nodes, yes, I would say that this is one place where the overlapping variant can work. So if I have multiple copies of the same ingredient, this is basically like saying I'm allowed to put it into multiple different cuisines. And so I think you could pretty much directly take those off the shelf. We have several different variants for overlapping clusters. Some of them, one of the variants that we studied, you're allowed to put down a budget for each node. And so in that case, you could associate one number for however many copies you have of each ingredient, even if that's different, right? And so if I have, I don't know, 7 watermelons, my weight is 7, and I have 2 jars of something else, I can put the weight of 2 right there. So that might work for that problem. Now, as for the substitutes, that's interesting. I have not thought about that. So if you can think of a good formulation for the problem, I would be really curious to see if vertex cover or linear programming or other variants of the problem would work for it. But that's one direction I haven't explored yet. But it sounds really cool. Yes.
Thank you so much for the talk. I work on knowledge graphs for language applications. Basically, I'm dealing with co-reference resolution, trying to form these clusters with some sort of hyper-edge and graph. So your idea of like removing salt and oil, which are common occurrences, like essentially like this gives me an idea to prune out pronouns like he, they, she. So that could be a good application. But what could you like talk about your experience on this aspects, like on applications beyond cuisines? You see any obvious applications in language or any other application at all? Thank you.
Yeah, thanks for the question. I confess I haven't really thought much about applications to language. So that's an interesting new application domain that maybe I should think about a little bit more for this problem. As far as pruning things out, though, yes, I think that almost every single application I can think of edge-colored clustering, you will want some sort of a way to prune out things that are not very interesting, or at least allow them to do overlapping clusters. So this pruning that we did, we really sort of realized at the time maybe we should be doing some sort of overlapping variant of this problem, but we're limited in how much we can do in one paper, and so for right now we're just going to prune. And so that was an expedient way to deal with things, and it was simple. And let me think of other types of applications. Well, so if you think of authors and papers and fields, not everyone fits. Actually, most people don't necessarily fit into one scientific discipline, right? And so in that case, you might want, I don't know if you necessarily want to prune out authors that are very prolific, but you might want to allow them to be associated with different categories. And actually, even though I did not have time to talk about this, there's another way to think about this edge-colored clustering problem that relates to something else that's been done by a different group, where what they were trying to do, under the surface, the algorithms end up being very similar. At least the problem ends up being similar. But what they're doing is they're basically doing something which is almost exactly equivalent to ECC, but they're not doing it so much to classify the nodes. They're sort of doing it as outlier detection, and they're trying to realize where, like, actually this color's not very meaningful. I should delete this, in some sense prune it, maybe to your question, because it's not really true that this is only green or this is only orange. And so without actually telling you about this stuff, I will say that there's another view on the problem which amounts to pruning, essentially, because of this realization that I'm not going to be able to cluster things perfectly. I should maybe prune some stuff. And maybe it's interesting to figure out what I should prune because it tells me something about that data object. So there, I've managed to twist your question into an excuse to use to talk about some of the slides that I didn't talk to during my talk. Great.
All right, well, if there are no more questions, let's thank our speaker again.
Thank you all.